Let us now look at the layout of a diesel electric power station. Obviously, by first look, you can see that it is a very complicated system, but we are going to try to simplify the understanding of this system. So, let us first start with this fuel tank. This is the storage fuel tank in which all the diesel fuel for the plant is contained. So over here you can see that this is the outlet port, and from this the fuel is transferred into the day tank via the transfer pump and strainers. So strainers are there to remove any impurities in this fuel which is stored in the fuel tank. So these transfer pumps transfer this fuel into the day tank, which is a tank which whose capacity is enough to sustain the operation of a diesel electric power station for a whole day. And then this day tank gets filled up, and there is obviously a pipe in that day tank to carry the excess diesel fuel if the tank is filled beyond its capacity. So this overflow pipe takes the fuel back down into the fuel tank if the filling of if the day tank is filled beyond its capacity. So in this day tank, we have a fuel which is used inside the diesel engine, and from this day tank, this fuel then goes via this pipe and a filter into the fuel injection pump, and this goes into the diesel engine. This right here is the diesel engine. So the fuel is going inside this diesel engine via this filter. Um, After this, we are going to look at this intake. The air is taken in from this air intake, and fresh air is going flown taken in, from the air, and then it goes through this air intake filter, and then it enters the diesel engine in the different cylinders via the engine manifold. Inside the engine, this air mixes up with the fuel and rotates the piston of the engine, and then the byproducts are sent as exhaust to the silencer, and they are emitted into the atmosphere. Generator is shown over here, and it is coupled with the engine shaft, and this generator rotates to produce electricity. Now let us move to the lubrication system of this engine. So lubricant oil is placed inside this lubricant oil tank, lubricating oil tank, and lube oil, we are going to call it lube oil. This lube oil is transferred into the diesel engine via the oil pump, and this oil then lubricates the parts of the diesel engine so that less friction is present inside them, and low heat is generated from them when they rub when they rub together. And this is the oil pump, and you can see that there are two pipes. There is also an auxiliary oil pump. The purpose of this auxiliary oil pump is to maintain the flow of lubricant oil through the diesel engine in case of failure of this main primary oil pump, or in case of failure of this line. So because we need to have a constant lubrication of in a diesel electric in a diesel engine. Then this lubricant oil flows inside this diesel power. Then flows inside this lubricating oil flows inside this diesel engine, and then from this diesel engine, this lubricating oil is sent into the filter and purifier to remove any particles which might have entered it during lubrication of the engine, and it is then sent into the oil cooler to be cooled and resent back into the engine. Then there is a heat exchanger which removes the heat from the oil lubricating oil via using water from a water source, and this heat exchanger then transfers the heat of lubricating oil into the water and then cools the water down, and then this water is pumped inside the generator, inside the diesel engine jacket as well, so as to cool it, and then the hot water is again pumped back into the cooling towers so that it can again be cooled down and used again. So this is the layout of the entire diesel electric power station. Obviously, it's a bit confusing, but you have to the main point of this whole layout is that you should be aware of all the components and see and you must be aware of what their function is and how the function of plant would be effective if they are not if they fail. So say if I ask you what would happen if the intake air filter is destroyed or it is clogged up, what would happen in that case? So you must be able to answer that question. Similarly, you must be able to answer what would happen if the primary oil pump lubricating oil pump failed. So you should be able to tell that the auxiliary pump would take its place. So these are the questions you need to answer, the conceptual questions about different parts of the power plant. Let us look at an example of diesel electric power station. So we have a diesel electric power station, and this power station has fuel consumption of 0.28 kilograms per kilowatt hour. So this means that for every 1 kilowatt hour energy generated, this plant consumes 0.28 kg of diesel fuel. The calorific value of fuel is 10,000 kilocalories per kg. So the calorific value of diesel is 10,000 kilocalories per kg. The overall efficiency, you need to compute the overall efficiency, and the efficiency of the engine if alternator efficiency is 95%. So let us look at the solution to this problem. Obviously, the calorific value indicates the amount of heat that is available from the fuel. So this fuel can produce 10,000 kilocalories for every 1 kg of fuel. So heat produced by 0.2 kilograms of fuel is obviously 0.28 times 10,000 kilocalories per kg, and that comes out to be energy in kilocalories. So that is 2,800 kilocalories. So fuel consumption of 0.28 kilograms per kilowatt hours. Obviously, I have already told you it means that the engine consumes 0.28 kilograms of fuel to generate 1 kilowatt hour of electrical energy. And we know from previous derivations that 1 kilowatt of hour of electrical energy is equivalent to 860 kilocalories of heat energy. So overall efficiency of the plant can be found by taking the ratio of output heat output electrical energy, the heat equivalent of output electrical energy, that is 860 kilocalories or 1 kilowatt hour, divided by the heat of heat that was released during combustion, which is 2,800 kilocalories, and multiplied by 100. So you get the overall efficiency of 30.7%. And obviously the engine efficiency would be the overall efficiency divided by the generator efficiency. You are given the generator efficiency, alternator efficiency, or generator efficiency is given to you. Overall efficiency you have already found from the calculations. So you can find the engine efficiency by dividing the overall efficiency with alternator efficiency as 32.3%. If there is any confusion why this formula is like this, we can talk about it in QA sessions. Now in this example, there is a diesel power station which has the following data. So fuel consumption per day is 1000 kilograms. So each day this plant consumes 1000 kilograms of diesel fuel. Units which are generated per day are given to you, 4,000 kilowatt hours. The calorific value of fuel is also given to you. Alternator efficiency is also given. Engine mechanical efficiency is given. So you have to estimate the specific fuel consumption. We are going to shortly see what this is. So specific fuel consumption in shortly I can tell you that it is the fuel consumption per kilowatt hour. So kg per kilowatt hour is required here. So that is quite simple. Fuel consumption per day is given to you, which is 1,000 kilograms, and the units generated are also given to you. So you can easily find the kg per kilowatt hours by dividing the 2,000 divided by 4,000. So 0.25 kg per kilowatt hour is the specific fuel consumption. Then you have to find out the overall efficiency. To find out the overall efficiency, you need to find out the output heat equivalent of electrical energy and the input heat which was produced by burning of the given amount of fuel. So heat produced by fuel per day is given by coal consumption per day into calorific value. So obviously this is wrong. The author has mistakenly written here coal, you should obviously know that this he means fuel. So fuel consumption per day is 1000 kilograms, and the calorific value of the fuel is 10,000 kilograms per kg. So the total kilocals which are produced in a day by burning of the fuel can be found as 10 to the power 7 kilocals. So electric output in heat units can be found by converting this kilowatt hour power into kilocals, which you can do by multiplying it with 860. So 4000 into 860 gives you 344 into 10 to the power 4 kilocals. Overall efficiency is simply the ratio of the two. So 344 into 10 to the power 4 divided by 10 to the power 7 kilocals gives you 34.4% overall efficiency. Then engine efficiency is given to you, that you can find out. Engine efficiency is not given to you, but overall efficiency has been calculated. uh, and you also know the alternator efficiency. So engine efficiency can be found by dividing the overall efficiency by the alternator generator efficiency. So engine efficiency comes out to be 35.83%. Now, what you are required to do is you are required to find out the thermal efficiency of the engine. Now, in this engine, you can see that there are two portions of this engine. One is the thermal portion where the diesel fuel is burnt to produce heat energy, and then there is a mechanical portion of the engine, that is the shaft which produces the rotations. So the total efficiency of engine is a product of engine's thermal efficiency and its mechanical efficiency. So mechanical efficiency of engine is given to you, that is 95%. Thermal efficiency you have calculated. You can calculate thermal efficiency by dividing the engine efficiency by the mechanical efficiency of the engine. That gives you 37.71%. Again, if you are unclear about these efficiencies and their products, we can discuss them in detail in the QA sessions. This is another example. A diesel engine power plant has one 700 kilowatt and two 500 kilowatt generating units. So a diesel electric power plant has one 700 kilowatt unit and two 500 kilowatt generating units. Fuel consumption is 0.2 kilograms per kilowatt hour, and calorific value of fuel is 10,200 kilocalories per kg. You have to compute the fuel oil required for a month of 30 days. So you must find out these requirements so that you have appropriate oil quantity stored in the storage tank. And then you also have to find the overall efficiency. The plant capacity factor is also given to you as 40%. So maximum energy that could be produced by this plant is given here. Like, you can produce maximum energy from this plant. Power is given to you. So there is one 700 kilowatt unit and two 500 kilowatt units. So total kilowatts in this plant are 1700 kilowatts. You have to multiply these total kilowatts with the total number of hours in a month, which comes out to be 13 to 24, and that comes out to be 1.224 into power 6 kilowatt hours. So maximum energy that could have been produced is this. Actual energy that is produced, it depends on the plant capacity factor. So actual energy production is plant capacity factor into maximum energy that could have been produced. So 0.4 into that amount you have already found, and that gives you 489,600 kilowatt hours. So you have to find out the monthly fuel consumption, and that would be specific fuel consumption, which is kilograms per kilowatt hour, into actual energy which has been produced. So that will give you the total kgs of fuel which you require. So so the specific fuel consumption is 0.28 kilograms per kilowatt hours, and total number of kilowatt hours which are produced are given here. So you get the total number of total amount of fuel required as 137.088 tons. It was 137,088 kilograms. So I have converted those kilograms into tons. Note that this is not the weight of the fuel, as weight of any quantity is expressed in newtons. This is the mass of the fuel. So monthly plant output is this 489,600 kilowatt hours, or the monthly plant output will be this output multiplied by 860 kilocals. So you are converting the kilowatt hours into kilocals, you get these kilocals. So the total heat energy input would be the fuel consumption multiplied by calorific value multiplied by actual energy that was produced. So 489,600 kilowatt hours were produced. Specific fuel consumption is 0.28 kilograms per kilowatt hour. So, and the calorific value is 10,000 kilocalories per kg. So, multiply all of them together, and you get a heat input for a month in kilocalories. And then you can find out the overall efficiency as the monthly plant output divided by heat energy input, and that gives you 30.11%.